Welcome to this new episode of Ask Stago, the podcast dedicated to provide expert answers to your expert questions in hemostasis. I am Audrey Carlo, and I'm glad to co-host today's episode with Cécile Hourquet. In our past podcast, we mentioned some assays using snake venoms, for example, Russell Viper venom for the lupus anticoagulant diagnosis. It is then time to question how venoms actually interact with coagulation cascade and how useful they can prove for science, but also for assay or drug development.
And Audrey, we are lucky to have as a guest Dr. Bryan G Fry, a.k.a. Venom Doc. Dr. Fry, you are currently Associate Professor at the School of Biological Science of the University of Queensland in Australia, and you have a passion for venom animals and venoms, living and working with snakes and other deadly scorpions. I think we could not dream any better guests to talk about the subject today, so thank you very much for being here and welcome to Ask Stago.
Oh, well, thank you very much for having me.
Hello, Dr. Fry, and thank you so much again for having accepted our invitation. I have a first question for you. How many interactions of snake venoms do you know with coagulation, or how many have been identified already?
With snake venom, anywhere reachable in the body by the bloodstream is fair game. And certainly the blood pathways have been something that's been hit on multiple occasions and sometimes convergently with different snakes evolving very similar toxins independently of each other to accomplish the same goal. And that's because the target provides the selection pressure for the evolution of the toxin. So if there was, for example, a snake toxin that caused cancer, yes, it would kill its prey, but it would take so long it would be meaningless. However, destroying the blood coagulation is an excellent way to kill this prey. So snakes have evolved to become procoagulant, basically killing by the induction of massive catastrophic strokes, and other snakes have evolved to become anticoagulant, basically Ebola with fangs. So with the procoagulant snakes, two main areas have been hit on multiple occasions, and that's the activation of factor 10 into 10A, which of course then continues on until you end up with nice big blood clots at the end of that. And then also the activation of prothrombin into thrombin, and then yet again the generation of additional blood clots. These two particular targets are very useful because they're so far down the clotting cascade that the difference in time between activating them and the final fibrin clot is very short. As opposed to if you activated factor 12, it certainly would produce a nice, strong, well-ordered clot, but because it has to go through so many more steps, it'll take longer. It's much like writing computer code, where the fewer lines of code that you write, the quicker the task gets done. And so same thing with turning on the clotting cascade. The further down you can do it, the quicker the desired outcome will occur. So we have found, we're actually just about to publish on the first activators in snake venom of factor 12, factor 11, factor 9, and factor 7. We've just discovered these in different snake venoms, actually.
And so you clearly explained the so-called procoagulant venoms. How about the anticoagulant ones?
Now, the anticoagulant side of things, there's a lot more freedom there because if you block the extrinsic or intrinsic pathway at any step, it's going to have the same outcome of anticoagulation. So with the anticoagulants, every single point on the clotting cascade has had at least one anticoagulant toxin identified. So of course, these kinds of impacts are of huge importance from a clinical perspective where, if you have a massive stroke, you're going to end up with a permanent injury or death. Similarly, if you have patients that are bleeding internally, they're going to die. So with these kinds of compounds, there has been use for them therapeutically, both as breaking up strokes and also preventing strokes. So you have ones that, like Draculin from the Venom of the Vampire Bat, coolest name ever for a compound, is used as a stroke buster. So it's breaking up blood clots much more efficiently than just about anything out there. And then you have other compounds that are being used for the treatment to prevent strokes because they're binding to platelets and preventing platelets from aggregating.
It's really interesting how, when we talk about all these species, we are really afraid. We are thinking about the snakes, the bat, the ticks, the fleas, the frogs, and all the danger that they have. But you have twisted about how they can be useful for us, which is really interesting. Is there an importance? It's really a question out of the blue, but we know that snakes will more use this type of mechanism, whereas bats will more use, or is it like all these species can have different type of venom depending of the subspecies that you can have?
It depends on what the evolutionary selection pressure is for the use of the venom. So in the case of a vampire bat, it's not trying to kill its prey, it's just trying to keep the blood flowing. So it has anticoagulants, but it also has very powerful vasodilators that dilate the very small blood vessels on the skin, which keeps the blood flowing. And then also they're breaking down any blood clot that does form through the aforementioned Draculin.
Okay, so now we clearly understand the secret power of vampires then. Dr. Fry, we know that sometimes the bite is made to kill the prey and not only to have a blood meal. You probably have some examples of the process of mechanisms there?
Something like a rattlesnake that is trying to kill a prey, so it's causing a complete destruction of the blood chemistry, while at the same time it has these destructive enzymes that are basically like, the acid blood of a alien in the movies, where it's causing holes in all the vascular walls, and therefore the blood is flowing out through those holes. And because the blood chemistry is destroyed, blood clots can't be formed to fill those holes, and therefore enough fluid leaks out of the arteries that you get a massive catastrophic drop in blood pressure, and that's what ultimately kills their prey. So it has to do with what is the use of the venom. Is it just parasitism where you're trying to obtain a meal, or is it prey subjugation where you're trying to immobilize and kill your prey?
And Dr. Fry, we can hear how passionate you are about our subject. And just to mention, you've been working with a biological science school, so I assume your research is driven by the understanding, but also hearing you, it's almost driven by understanding also the evolution and how species interact one with another, right?
Very much so. That's what really drives us. We're complete geeks. At the end of the day, our fuel is this almost childlike curiosity for these animals that we think are so incredibly cool.
But also we can see that you can take like things for drug design and the development, if I'm right, to this perspective.
Oh, without a doubt. It's the kind of thing that will naturally emerge from a large enough high quality data set. So we're interested in the evolution, which means we're seeking out the biodiversity hotspots. And of course, if you want to find a novel compound for use as a therapeutic, as a lead compound in drug design and development, you're not likely to find it from something like a European viper that has been intensively researched for decades, where that ground has been raked over very, very well. It's not to say that there isn't something useful in there. It's just you have to spend a lot more time and effort to find it. Versus if you look at an animal that is completely unrelated to anything else that's been studied, there's going to be a lot more low-hanging fruit, and you're going to have a greater opportunity to find something novel very easily. So research is like anything else. You want the best return on your time and money. And therefore, if you're trying to find something novel, look at a novel animal. This is a natural resource. This is a biobank that we can only develop life-saving drugs from it if that ecosystem is still intact and if those animals are not extinct. So, for example, if you know of anybody who takes high blood pressure medication, odds are they're taking captopril or one of its derivatives. That was invented about 45 years ago, but it remains today a $10 billion a year market. It's been one of the top 20 drugs of all time. Its medical and economic importance cannot be overstated. It's up there with aspirin for its impact. Well, that was developed from a snake toxin, from one of the lance-headed vipers of South America. So we can't develop wonder drugs like that if they're, not around.
And, we have listeners, so how would you like them to participate if they can participate in some way in such like initiative?
Yeah, well, I think the way to do it is through education and inspiration, more inspiring change rather than forcing change. It's much easier to have a carrot than a stick.
Yes, very interesting this comment about the carrot and the stick and the sustainability of the whole economic and ecosystems of Venoms. Dr. Fry, we're close to the end of our podcast. Would you have any take-home message for our listeners today, maybe around hemostasis or the impact of Venoms on coagulation?
Oh, well, certainly that there's so much more that we can discover. We barely started scratching the surface of that. Certainly the take-home message is, take advantage of the technology.
Thanks a lot again, Dr. Fry, for having shared a bit of your passion with us and our listeners today. And thank you for all the literature sources you referred to us. Those sources will be in the podcast description box as usual. And to our listeners, please feel free to send us any question that you may have at our email address, ask@stago.com, and we'll be happy to address it in the next episode. See you next time.
This podcast is brought to you by Stago. Diagnostics is in our blood.